want to first thank the organizers, not just for having me, but for this workshop, which I think has had just a really exceptional collection of the diversity of perspectives. This is amazing, and I'm really enjoying the conversations we're all having. So I was invited to talk about traceability and primary standards for alpha emitters used in targeted alpha therapy. My name is Denis Bergeron. I'm from the NIST in Gaithersburg in the US. Portions of this work were supported by these companies, and NIST does not endorse commercial products. So I'm always concerned when I'm part of a lineup with so many great speakers that I'm going to be giving the same talk as 3 other people. So my solution to that this time was they gave me a title. The title is the outline of my talk. I'm going to stick to that. So I was asked to talk about traceability and primary standards for alpha emitters used in targeted alpha therapy. We'll start with traceability. We saw a little bit already that somebody was giving the same talk as me. Brian covered the definition for traceability, but Roman said it is okay to repeat a little bit. So I will take his advice, and I think I will join the audio. No. So metrologists really love pyramids, don't we? It's So metrological traceability, we're here at the BIPM. We'll turn straight to the VIM, the International Vocabulary of Metrology, for the definition, which will be the property of a measurement result whereby the result can be related to a reference through a documented, unbroken chain of calibrations, each contributing to the measurement uncertainty. So there's some key things there, and Brian talked about this some yesterday, but this is the measurement results. There's this chain of calibrations starting from one place, whether it's the National Metrology Institute or on down the pyramid. And a key component to all of this is that if you're going to compare 2 numbers or 2 measurements, the comparison means nothing without a statement of uncertainty. So a traceability chain has to have these uncertainties. So we'll go to the pyramid that metrologists love so much. At the top of mine, I put the International System of Units. So the National Metrology Institutes and the designated institutes too. But like NIST, it's our mission to realize the Becquerel, to realize the International System of Units. From NMIs, traceability can proceed to secondary calibration laboratories, onto production sites, radiopharmacies, and to clinical sites. I've thrown these arrows onto the side of my pyramid to show that in some or in a lot of cases, we can have production sites or even clinical sites working directly with NMIs to establish a direct traceability. And you can see the advantage there is fewer links in the chain, potentially tighter uncertainties. So when I talk about traceability today, I'll talk about a couple of mechanisms, direct calibration, but then I also want to talk a little bit about benchmark calibration factors, calibration settings, and I want to talk about, without stealing Sean's whole talk, decay data as well. So back to my outline, my title, really to dive into this very deeply, we have to start at the top of the pyramid, which is also the base of the pyramid. And if you ask me how the base can be the top, I'm just going to stare blankly, and we'll have to move on after a minute. So primary standards are the top of the pyramid here. We can again go to the VIM for our definitions. A primary measurement standard is one that is established using primary reference measurement procedure. That's not very satisfying, so we need to go to that definition too. We can stick with the VIM since we're at the BIPM. And a primary reference measurement procedure is one that's used to obtain a measurement result without relation to a measurement standard for a quantity of the same kind. If your head is spinning, that's okay. The point here is that it's our mission at the top of the pyramid of this traceability chain to measure the Becquerel without calibrating to another Becquerel. So we're talking about measurement techniques that are internally consistent, that are self-calibrating. I'll give some examples. We'll talk about how we can approach that and what we do at places like NIST in order to make that first link between what we're doing and realizing the international system of units, realizing the Becquerel. The last part of my outline, my title is 4 alpha emitters used in targeted alpha therapy. We've heard a lot about this already. So we know that in targeted alpha therapy, we need to measure the administered activity. This is the starting point for everything that we do or that we want to do. This is the key input for dosimetry. Whether we're doing it yet or not, it is a goal. So we need the administered activity. It's also the key input for quantitative molecular imaging, whether that's for diagnostic purposes or part of a dosimetry scheme. And I know that we heard already from Romain, but for imaging or for therapy, our goal is to administer enough activity to do the job and not more than that. So we care about precision measurements here. The SI unit for activity is the Becquerel. And the Becquerel over here is defined as decays per second of a radionuclide. We've done a lot of definitions so far. Looking to the VIM, I think we'll keep on theme for a minute longer and keep defining things. We'll define the Becquerel now. Again, this is decays per second of a radionuclide, and there's actually a lot packed in to that little definition. The first goal, the first task that we have when we're measuring activity is to define what a decay is. And as we know, for a lot of the radionuclides that we care about, that means a lot of things. I threw up here just, I'm not saying actinium-225 is my favorite, but I'll use it as my example here. Actinium-225 decays mostly about 52% to the ground state of francium-221, right? The other 48% is split between 47 excited states in francium-221 with all of these attendant gamma ray emissions. So a decay for actinium-225 is a complicated thing. It means a lot of different things. And we get lucky when we're doing our measurements because actinium-225 is at least 100% alpha decay. A lot of what we're talking about is not, and we have to deal with both alpha and beta decay paths for one radionuclide. That's still a decay, and it still counts in our definition of the Becquerel. So our methods have to be designed to account for all of that. The next part of the definition is this per second, and that's just counting the decays. And of course, when I say just, that is meant to be a joke. This is all of the measurement. This is all of our work, right? And as I alluded to just a moment ago, our counting methods have to be appropriate to the decay types, whether it's alpha, beta, electron capture, all of these things. We have to figure out how to measure this particular thing. And we have to have good efficiency models to tell us when we're missing counts. This is where most of our work goes. And of course, it comes back to having good decay data too. Our efficiency models are built on the decay data. The last part of the definition is of a radionuclide. And here I always insist this article A is so important because we don't add becquerels of multiple nuclides. And when I say we, I mean we don't, and you shouldn't either. I see this sometimes where people will talk about a alpha decay chain especially, and they'll sum the becquerels to give you a total alpha activity. And okay, you can define alpha activity or alpha emission rate or something. And if you define it and you want to use it, okay, but don't call it becquerels because becquerels are for a radionuclide. We don't sum becquerels like that. It's not a thing. So in the decay chains that we're dealing with right now, what that will mean is in our efficiency models, if we're trying to count for actinium-225, we know that we have counts that are contributed from the progeny. If we're at equilibrium, we know what those ought to look like. I'll talk more about that as we go. And it also means that actinium-225 is another good example where we have famous impurities. We have to account for those and the counts that they are contributing to our measurements so that when we describe a becquerel, it is for a radionuclide where the A is singular. So starting in about 2005 with work on radium-223, and I'm not saying this is when the world of targeted alpha therapy started or alpha therapy started, but at about this time, there was a new wave of interest in therapeutic radiopharmaceuticals. a company called Algeta came to NIST and asked us to develop a standard for radium-223. And since then, NMIs have been pretty busy looking at a lot of these alpha emitters that are of interest for medical applications. There's a recent review article. I think a couple of my co-authors on this are in the audience today, along with Karsten Kolsert from the PTB in Germany. And we kind of gave a snapshot of the current landscape as far as primary standards for alpha emitters in medical applications. Medically important alpha emitters. I'm sorry if I've excluded your favorite on this slide, but here's a few of the decay chains that we've looked at and that we've been focused on at NIST in recent years. In particular, the members of these decay chains that we've looked at include the thorium-227, radium-223, radium-224, lead-212 and bismuth, and most recently we've been working a little bit on actinium-225. So primary methods for targeted alpha therapy activity standards. This is taken straight out of that review article that I alluded to a moment ago. And I kind of like the way that we introduce primary methods for alpha emitters here, because we tell you, here's what a primary method is. We look at the VIM definition and we say, define solid angle counting is a really classic, good example of a primary measurement technique, because it's just the decay data and the geometry of your detector. And then we say, but we're not going to talk about that. Nobody's used defined solid angle counting for any of these radionuclides. It's all liquid scintillation based methods. So we have this nice bait and switch in the review, and I've just done it to you here today. I will be talking about liquid scintillation based methods as well. Liquid scintillation. So for alpha emitters, we assume 100% detection efficiency with liquid scintillation. So if we have a 4-pi detector, 100% efficiency, great measurement for alpha emitters. The way liquid scintillation works is we put our radionuclidic solution into a liquid scintillation cocktail. We use surfactants and stuff to make a nice homogeneous detector. The radionuclide decays, and we get alpha or beta particles. There's some quenching mechanisms. Energy is transferred from this decay into the solvent molecule. There's some quenching mechanisms. The fluor molecules then are excited by the solvent molecules, and they relax, emitting optical photons. There's some quenching mechanisms. We have to correct for all of these. But in the end, what we're getting is the deposition of energy from these alpha and beta decays, optical light, which we can detect really efficiently with photomultiplier tubes. So we have a real nice approach to counting. I mentioned just a moment ago that for alpha emitters, we have 100% detection efficiency. We love the short range in medicine. We love the high energy in medicine. And liquid scintillation counting, that gives us a whole lot of optical photons every time we have one of these alphas appearing in our solution. So there's always caveats. And in this case, there's a little bit of loss to the walls, but we can correct for that, and it's really small. So when we talk about challenges for liquid scintillation measurements, we're talking about targeted alpha therapy. You wonder, what's the big deal? What is the challenge if you're detecting with 100% efficiency? So that's where I'm going to focus for the next few minutes. And we're going to talk about the decay chains, where the progeny, of course, includes some beta emitters. The betas will be detected with less than perfect efficiency, so we have to account for that. We also have the progeny in these decay chains that include some short-lived nuclides. This makes some interesting things happen in our measurements. We have to account for that. And then I'll talk briefly about pre-equilibrium measurements, where the counting efficiency, I keep saying counting efficiency. I'm not sure if I've defined this, but when I say efficiency, I'm talking about counts per decay, right? Okay, so we'll have a changing counting efficiency as a function of time when we have pre-equilibrium decay chain. Then we'll talk a little bit about impurities with breakthrough and co-produced isotopes. So the primary method that I like to talk about for liquid scintillation counting is the triple to double coincidence ratio method for liquid scintillation counting. In this method, we have a 3 photomultiplier tube system. Most of the time, these are going to be home built at the various metrology institutes, although there are commercial products out there. They have the 3 PMT set up, and we can talk for hours about whether they're using the method that I'm describing. The key here is that we've got these 3 photomultiplier tubes, and we can set up nice timing electronics to measure coincident events. So we're going to see a flash of light, and we can see a coincident event in either 2 of the photomultiplier tubes, a double coincidence, or in all 3 at the same time, a triple coincidence. So if we count up the number of triple coincidences over a period of time, count up the number of double coincidences over the same period of time, we get a nice ratio, this triple to double coincidence ratio. And by definition, those count rates are going to be equivalent to the efficiency for triples events over the efficiency for doubles events. So now we can play sneaky tricks as metrologists and do things to vary the efficiency. Like we can apply neutral density gray filters to the outside of our LS vials, knock out some of those optical photons to reduce our overall counting efficiency, right? And if we can do that a few times, we can start to build a little curve where we're knocking down the efficiency. It reduces the triple to double coincidence ratio. If we have a few points, we can now build something where we extrapolate to a triple to double coincidence ratio of 1. The only time, of course, when the efficiency for triple events can equal the efficiency for double events is when the efficiency for all 3 photomultiplier tubes is perfect. We'll have an efficiency of 1 for any single event, which means 1 for any doubles event, which means 1 for triples. TDCR equals 1. That means that our count rate at this point right here is equal to the decay rate. The decays per second for our radionuclide means that we just realized the Becquerel without ever calibrating our system with a radionuclidic source. So this is an internally consistent, self-calibrating approach to liquid scintillation counting, and it's one of our workhorse primary methods in radionuclide metrology. Now, in practice, of course, I've lied to you, and it's much more complicated, but we have really good models, and we're able to approach all of this and make the corrections so that we're able to realize this in a true and good way. One of the good models that we have is this MyCell2 Monte Carlo-based approach for calculating liquid scintillation efficiencies for beta emitters for electron capture nuclides. We input the nuclear decay data and some features of the geometry and the scintillation process, and we pull out efficiencies. We won't talk about that today. Instead, I'll give an example. Here's an example with radium-224, which is not my favorite radionuclide, but it is a good one. In this instance here, we see that our experimental triple to double coincidence ratios are in about the 0.99, 0.995 range. And those correspond to a counting efficiency for radium-224 of something like 5.65 counts per decay of radium-224. And so we have more counts than we have decays, right? And that, of course, is because radium-224 decays in a chain. We've got all of the progeny here contributing counts to our liquid scintillation measurement, and we have to account for that, which we can do following the Bateman equations. We won't solve them in real time today, but we'll put the solutions up. In this instance, the half-lives all conspire in such a way that we reach equilibrium after, let's say, 5 days. But we can see that we have this period of ingrowth where measurements are more difficult, which means that in metrology, we're happiest if we can do all of our measurements out here after we've reached equilibrium. The beta decaying nuclides that we would have to account for that have liquid scintillation efficiencies less than 1 are the lead-212, which is listed twice, and thallium-208. But it's a little bit more complicated than just that. We can't just sum those Bateman coefficients and call it our, excuse me, we can't just sum the Bateman coefficients and the efficiencies for the betas and call that our predicted efficiency, because we have funny things that happen with the short-lived progeny. So in this decay chain, we have a 300 nanosecond polonium-212. That means that if we miss the beta decay of bismuth-212, because it doesn't have a perfect efficiency, then very soon afterwards, we expect the decay of polonium-212, which is an alpha emitter, to come. So we could, as a first approximation, count the bismuth-212 and polonium-212 as a single pair and call the efficiency for that 1. But funny things can happen because of that 300 nanoseconds. Here's the case where we have a decay event from bismuth that we catch in 2 of our photomultiplier tubes, and the polonium decay comes a little bit later, but it's within our coincidence resolving time. So it looks like a triple event. But you can imagine, depending on what we set for this resolving time window, that very often this could happen outside, but it could still happen within our dead time, which is another tricky thing. Here's the actinium-225 chain, which has some short-lived members in the progeny. Things get a little bit complicated here because we have decay events that can happen within our imposed extending dead time for our measurement. We have to make what Karsten Kolsert has termed these survival corrections, which fit this form. And I put up here the astatine-217 as well, because I think it's interesting. We did some work with autoradiography technique, these IKID detectors that Brian can tell you about. And the shutter speed on that is operating at about the range where this 32 millisecond astatine-217 decay comes into play. And again, these survival corrections that we make for some of the very short-lived radionuclides pop back up as we get to some of these longer time scales in different measurement techniques. So that's kind of interesting. So we're making corrections. We know how to account for beta emitters. We can make the various corrections we need to account for the behavior of the short-lived radionuclides in these chains onto pre-equilibrium measurements, right? So we know for things like radium-224, where the longest-lived progeny, lead-212, has a half-life of 10.6 hours, it's going to be a little more than 6 days to get to true equilibrium with a bunch of 9s in the 99.99 whatever % of final equilibrium. Separated from its parent, we could look at lead-212. The longest lived progeny there is bismuth-212 with an hour half-life. So we get to equilibrium in about 12 hours. So again, as metrologists, we want to make our living in the easy region, making the measurements after we've got to equilibrium so that we have fewer corrections and less uncertainty due to the timing or due to the efficiency of the separation. Make things as simple as we can. So Dark Helmet once said, if there's one thing I despise, it is a fair fight. But if I must, then I must. Thorium-227 is the case where we must. Thorium-227 won't get to equilibrium for us to make our easy measurements. So we've got to measure while things are changing, right? So this is plotted out here as a generic instrument response. I'm pretty sure I stole this data from one of our ionization chamber models. So you can see that while thorium-227 is decaying, radium-223 and progeny are growing in and then decaying. So if we make ionization chamber measurements with thorium-227, if we make liquid scintillation measurements with thorium-227 shortly after separation, then we watch as our count rate shoots up for days, right? For almost 20 days, our count rate is increasing. It's a strange situation for those of us who are used to decaying radionuclides. But then after that, we start to go back down. So we have to have good models of the instrument response, and we have to have good input nuclear decay data, especially for these half-lives, in order to have good models of what these curves are doing. In this instance, we were able to develop a primary standard, again, based on triple to double coincidence ratio counting. I'll walk through this quickly because I think it's fun, and you caught me. We got to my favorite radionuclide, but not for any medical reason, just because it's a fun challenge from the metrology perspective. Right, so here's a snapshot of 1 week where we have a triple to double coincidence ratio efficiency curve that looks like this. Our efficiencies at this point are in the neighborhood of 3 counts per decay, right? And these are using our nice micelle model. we can do this a lot, and we can start to see that strange things are happening, right? This triple to double coincidence ratio that we're monitoring, we predict over time that where we started with thorium-227, pure alpha, so 100% detection efficiency, TDCR 1, that decreases over time as the beta emitting progeny grow in, and our counting efficiency at the same time is increasing because we have the contributions from those progeny. So the progeny are increasing the efficiency, but reducing the TDCR because they're not increasing the efficiency with an efficiency of 1 for each one of them. We have some beta emitters in there. It's tricky, but again, it's fun. So we can map this out at 1 week, 2 weeks, 3 weeks, and see that our efficiencies are going to be increasing over time while our TDCR shifts down. What we did in this instance was adopt a single figure of merit model. We said if we assume that the liquid scintillation source is stable, and we did a bunch of tests to make sure that that was a decent assumption, then the observed TDCR will change as the beta emitting progeny grow in. And our efficiency model should track how all of that goes. The slope of the curve is predicted by the counting efficiencies for the beta emitters, right? So the free parameter can be adjusted so that we fit our model to the experimental data. So I've just illustrated here that we can use different inputs for our model to say, no, that's not the right efficiency model. No, that's not the right one. Here, I fit the time evolution of my data really well, and that's the right figure of merit, this right kind of global efficiency, if you will, to give me my counting efficiencies over time. I would test that, of course, by measuring here and here and here and getting the same activity using those efficiencies. That's what we did, and it worked very well. I think we got a combined standard uncertainty there of less than 0.3% in the final primary measurement. All right, so we talked about some of the challenges in decay chains onto impurities. The issue of breakthrough in column-produced material is always something that concerns us. It's very difficult to see early on, but we're waiting for equilibrium and then trying to measure for a little while so that we get as many measurements as we can. When we were working on radium-224, thorium-228 was insignificant, except for this one time when we had a much larger contribution than we expected. We actually got on the phone with Roy Copping at Oak Ridge National Lab. Turned out that particular batch, they had tried out a new separation technique, and he said, maybe we're going to go back to the old one. So we can work together with colleagues to address problems, but these are the things that we're watching out for, and again, that we have to correct for in our measurements. I don't want to spend too long on this, but when we, in the radium-224 case, looked to the literature to see how people had been dealing with thorium-228 breakthrough, we found that there's this common idea that if your source is decaying with the right half-life, then you don't have to worry about breakthrough of long-lived impurities. And that was a little concerning to us. I've shown one case where that's the claim, another case where they said that, but they also did a lot of additional measurements with alpha spec, liquid scintillation, to make sure that their radiochemical purity was what they thought. So this is a good example of how to do it. So this claim about half-life comes in because it's difficult to detect thorium-228 in radium-224. You'll never see it in a sodium iodide spectrum. That's not where the gammas are coming from. In high purity germanium, if you're doing good gamma spec, then you can see the thorium-228 peaks, but early on, they're going to be hidden in the Compton background from the other gamma rays in the decay chain. So it gets very difficult to see this at all early on, even with high resolution gamma spectrometry. So can you use the half-life to detect these parts per million level breakthroughs? So If you're measuring pre-equilibrium, then you have a lot of corrections. This is a difficult half-life measurement. Let's throw that out and say that most labs are not going to be able to do that. But people can, after equilibrium, watch a decaying source and fit that to the exponential decay and try to make a half-life measurement, right? But it turns out that these half-lives are actually going to look fairly robust against thorium-228 breakthrough. You don't see a big difference. So here's two examples measuring for 24 days, so out to day 30. This is probably impractical for most end users, or just measuring for 15 days. So you can catch parts per million level breakthrough outside of the stated uncertainty on the half-life if you monitor for 24 days, but it doesn't show up if you monitor for just, say, 9 days in this case. So the question we asked was kind of, what can we know? What kind of breakthrough can you detect? At what point? When can we know it, right? So monitoring the half-life can give you sensitivity to parts per million level thorium-228 breakthrough if you can distinguish a deviation of just 2 sigma from the evaluated half-life. Okay. So this is to say, you can do this if you are the best in the world at measuring half-lives, and if you can measure for 50 days. But nobody's that good, of course. And I took a bunch of gamma spec half-life determinations from our lab. I should say these weren't all dedicated efforts to measure a half-life, but I think it's fair to say that not all end users are making dedicated efforts to make a metrology level half-life determination, right? And you can see there's a lot of spread. The uncertainties are quite big. Put that up next to the half-life measurement using very well-controlled ionization chamber at the PTB in Germany, or the ionization chambers that we maintain at NIST. And you can see this is very difficult. There's a big spread in the data set, and the estimated uncertainties vary. So catching breakthrough at levels that we care about becomes a challenge. Gamma spec can't do it. Monitoring the half-life makes it impractical in most cases. And this is a problem for any column-produced targeted alpha therapy nuclide, whether it's lead-212 from radium-224 or actinium-225 from thorium-229. Of course, other impurities besides breakthrough of the parent matter. This is a serious concern that we heard about with actinium-227 impurities and actinium-225. I think it was also mentioned that these similar issues and the regulatory concerns that come with them have been familiar recently, thanks to lutetium-177 metastable impurities and lutetium-177 radiopharmaceuticals. I think I just finished all of the challenges to the measurement portion of the talk. So I'm going to talk about quickly some of the recently standardized alpha emitters that we've done at NIST. And we heard yesterday about what's going on at some of the other metrology institutes and submissions to the BIPM for comparisons. At NIST recently, we've looked at radium-223, radium-224, lead-212, thorium-227, and actinium-225. Just a snapshot of the few of the reports that we put out on those to give a fairly typical uncertainty budget for one of these TDCR-based primary standardizations. You can see that our counting statistics will always be one of our biggest components of uncertainty. After that, we have the model uncertainty, and we'll look at repeatability, preparing multiple sources. In this particular experiment for lead-212, it was designed to minimize the contributions from the half-life because there were some concerns there. The nuclear decay data can often be one of the largest contributors to our combined standard uncertainty, whether that's the uncertainty on a alpha beta branching in the chain or particular emission intensities and how they come into the models. And then we have uncertainties for our efficiency model itself and our mass uncertainty that links the sources prepared for primary counting to the sources that maybe you would measure on an ionization chamber. So the recently standardized alpha emitters at NIST, we're achieving combined standard uncertainties, typically below 0.3%. The most recent standardizations that we've done were for thorium-227. This is not yet published, but the combined standard uncertainty here winds up being time dependent because thorium is so much fun. And for actinium-225, we've achieved a combined standard uncertainty of 0.27%. So the traceability part comes, we've realized the becquerel, and now we disseminate the becquerel. Using liquid scintillation-based primary methods, NMIs, including NIST, have developed standards for a growing list of the nuclides that we care about in targeted alpha therapy. Dissemination of these standards from the NMI to the end users proceeds by a few different paths. Talk about that. As you know, end user measurements in most cases are going to be using a radionuclide calibrator or a dose calibrator, sometimes called. This is a reentrant well-type ionization chamber. What the technician in the radiopharmacy or in the clinic wants to see is a button corresponding to their radionuclide to push and then read the activity. So it's everything behind the button that we've talked about so far, and we'll talk about how to calibrate that button a little bit. The other common calibration or measurement method for activity would be gamma ray spectrometry, whether it's with a high purity germanium or with a well-type sodium iodide gamma well counter. That still comes back in many cases to our primary measurements, but this through the absolute emission intensities for the gamma rays that we care about. So back to the pyramid. Like I said, we're dealing now with the traceability part of the talk. And we have a couple of different approaches: direct, calibration, benchmark factors and settings, and decay data. So direct calibration can go two different directions. The first would be the example where an end user submits a source to a calibration lab, like NIST. And NIST would then measure the activity of the source and return a certificate for the massic activity of the source. So the local calibrations from the lab submitting the source can be adjusted based on the results in that report. So maybe you have your radium-223 that you measure on your radionuclide calibrator. So you think you know the activity, send it off, have it calibrated, and find out what the difference is between your measurement and the Metrology Institute. Great. The other approach is for the end user to receive a calibrated source. So this would be a source is prepared and measured at the Metrology Institute. It's certified for massic activity, and it's certified for the total activity in the vial or in the ampule. This is shipped out to the end user so that local calibrations can be performed with the source that they've received, that they know the activity. I put up here Jeff Cessna's contact information. So if you're in need of calibration services from NIST through either of these approaches, you can reach out to him and he'll answer, not me. So one of the approaches to these local calibrations that I mentioned would be the calibration curve approach. So I've shown here on the left a plot where the calibration setting, so you don't always have the nuclide button. You can also enter a calibration setting 472 or something on your radionuclide calibrator. If you have your source and you measure it at a series of settings, then you should get a plot that looks like this. I plotted it out here so that the activity that's red on the display is plotted as a fraction of a standard activity. One nice thing about this approach is you don't have to know the activity. You don't have to know the standard activity when you do these measurements. If you get that later, then you can still normalize the data that you acquired. If you find where this ratio is equal to 1, then the calibration setting that corresponds to that reading on your curve is your new calibration setting that allows you to make traceable measurements in the future. Another thing I like about this approach is that you can calculate an uncertainty for the fit based on the fit residuals. I'm a big fan of looking at the residuals and considering the uncertainty on your fit. The other approach is often called dialing in. This is possible if you know the standard activity at the time of your measurement. You can just put your calibrated source into your radionuclide calibrator and change the dial setting until you get to the one that gives you the right activity, and use that from now on. There are some practical considerations for this kind of calibration. The first would be that the geometry, the measurement geometry matters. And it's really key that the calibration geometry will match the measurement geometry. So if you get a 5 milliliter ampule shipped to you from NIST and you're going to be measuring in syringes forevermore, then the calibration setting you determine for that ampule might not be exactly what you need to measure syringes in the future. And there are approaches and methods that you can use to transfer from one geometry to another. And then another thing to consider is that you may find benchmark settings from the instrument manufacturer. So look in maybe the Capintec or the Veenstra manual will have a list of calibration settings. And these should be treated as a benchmark so that if you're establishing a traceable calibration setting for your instrument, you're hoping that it's close to this benchmark setting from the user manual or from a NIST publication, Bergeron et al. These should always be verified in your lab with your instrument, in your measurement geometry, and with your local shielding configuration. All of these things can affect the instrument response and disrupt that chain of traceability. So a traceable calibration means that we have this documented, unbroken chain of calibrations. So it's important to stress that using the setting from a manual or using a calibration setting from an NPL publication or from a NIST publication, that doesn't make your measurement traceable, right? We have to have this unbroken chain of measurements that Brian was describing yesterday. And that's how we achieve traceability. While we're on the topic, I think this lead-212 story is a really interesting one. This is a snapshot of my 1986 Capintec owner's manual, but in fact, this table is similar in newer models, and they're all related. But let's look at lead-212. We have a nice calibration setting here of 101 for lead-212 in isolation. But we have a note that it's going to decay to bismuth-212. Of course, we all know this. Lead-212, you're never going to measure it in isolation because you're just not quick enough, right? So it's fortunate that we can look a little bit lower down and we see that we have calibration settings for lead-212 in equilibrium with bismuth-212. Good. There's a couple of different ones here. This lead-212 says equilibrium after 8 hours, and the reading that you get with a setting of 158 gives the activity for lead. Good. You even have a special setting down here that you can use that'll give you the total activity of lead and bismuth. And as you'll remember from earlier in my talk, now we're adding becquerels and I'm wincing, but forget all of that. We have some options in the manual on how to measure lead-212. Good, so we go to the literature, and Elisa published this paper in 2020, and she said, you know, I had a NIST traceable source for lead-212, and I find a calibration setting of 662. And we're looking at the manual and thinking something is really crazy here. So it seems that these were theoretical calibration settings that Capintec gave. The settings neglect all of the progeny past bismuth-212. And of course, with this particular decay chain, the 2.6 MeV gamma ray from thallium-208 is going to account for the bulk of the ionization chamber response to lead-212 in equilibrium with its progeny. So we, we can look at some of those settings from the manual, see the kind of bias that we would get if we just blindly used those to assay our lead-212 source. See that we have a real problem. We can also see that the Napoli setting was a pretty good one compared to what we got at NIST. The settings that we found in the manual will give bias with a factor of 3 to a factor of 7. This is not insignificant. So for decay chain nuclides, you guys, we have to be careful when we're referencing especially theoretically determined radionuclide calibrator settings, because it's not always as easy as it sounds from the start. And here's from the NIST publication, the benchmark settings that we gave for a few models, where the uncertainty here is given as the uncertainty on the activity that you should expect, or that we expect in our lab when we measure with these settings. A quick word on pre-equilibrium calibrations back to thorium-227. The approach that was adopted by our colleagues at NPL that we also implemented at NIST was the idea of adopting a single calibration setting. Remember, thorium-227, we can't measure at equilibrium, so our instrument response is changing while we make the measurement. So if we adopt a single calibration setting, that means that we have to have a lookup table that gives us a multiplication factor for the reading. So I have to see what time it is now, how long that is from my separation time, and apply the appropriate multiplication factor to get the right activity. And I believe Andy is preparing a publication on this. And we also have a informal bilateral comparison that we're working on that'll include some of these data. Dissemination of standards by nuclear decay data. So if we write down the equation for the absolute emission intensity for a gamma ray line, we could put it in terms of the number of counts divided by the efficiency for a well-calibrated detector times the activity. And we have the activity standard because we just did the primary activity, so we can hand an ampule to Letitia and she'll measure it. Great. So the determination of absolute gamma ray emission intensities is going to support calibrations by gamma ray spectrometry in other labs. We also have opportunities to improve evaluated decay data where it's necessary, and to provide benchmarks to compare calibrations and standards between labs. So very often, Sean and I will get on the phone. We'll talk about, we got this emission intensity for this particular gamma ray line. So, oh, well, we're in agreement on our emission intensities, which means if we move backwards, that we just did an indirect comparison of our primary standards for activity. So that's great for us, but it also means that we're working together to provide improved emission intensities, which STIG wants, right? For some of these important lines that we want to use for downstream calibrations. And here again, I have to stress that a traceable calibration comes back to this documented unbroken chain of calibrations. So a measurement is not traceable to a NIST standard because it used an emission intensity published by NIST. There has to be the chain of measurements to establish that. Just as I think, getting to be classic example now of the importance of these reevaluated emission intensities in the field of targeted alpha therapy. I pulled the table here showing the emission intensities for the radium-223 chain. And you can see that the state of the measurements before a bunch of these NMIs started looking at the emission intensities again was not so good. In 2011, we have pretty big differences between the new values and the previous evaluated values. Big changes result in big differences in the assays that you would get by gamma spec now if you're using that as your approach to an activity measurement. So I think I'm just about done. We'll finish with the pyramid that we love so much. So again, my title was Traceability and Primary Standards for Alpha Emitters used in targeted alpha therapy. I hope that you leave with a little bit of a feel for what primary standards from metrology institutes look like, how we realize the Becquerel with these internally consistent self-calibrating methods like the triple to double coincidence ratio liquid scintillation method that I talked about. And then we talked about traceability, different approaches to that. And hopefully the big take home there is that we've got direct calibration or chains of direct and documented calibrations, and each link in the chain has an uncertainty. I'm not going to be able to thank everyone, but I want to just throw up some names here from the radioactivity group at NIST and some of our collaborators, many of whom are in the room. Thank you all. And if you have students or postdocs who are looking for opportunities in metrology, find me afterwards. Thank you.